okay, all we want to do here is to try to practice doing some things that we're going to need a lot. The first is being able to sketch, left end and right end, just for some, I don't know, maybe as many as 6 rectangles. I think that's probably about what people actually have us do. So what I want to do is just, I'm going to draw a graph, drawing a graph of anything I want. Yodi, 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 yodi. How about like that? Yay, right? And let's say we go all the way to say 5. And someone wants me to draw the rectangles corresponding to left 6. Well, here we go. What do I need to do? I'm supposed to have 6 rectangles, so I have to divide this whole interval up into 6 little pieces. So I'm going to divide it in half, and then a third and a third, and then a half, and a third and a third. I think that's reasonably close. Now I want left 6, which means I need rectangles. What I usually like to do is this is better on a chalkboard, just try to draw the sides of the rectangles and then try to figure out where the tops go. So I'm just going to sit here and I'm just going to draw the sides. I'll worry about where the tops go when I'm done. Every rectangle has sides and a top, so I won't have wasted any effort. Here we go. If I want to go left 6, what I need to do is now go to each little interval, go to the left end point, go up to the graph, and draw the top. So this is the first rectangle I get for left 6. A second rectangle, I go to the second interval, I go to the left end point, I go up to the graph, top to top, top to top, like that. And then like this, and like this, and like this, and like this. Now, by the way, you see right away what one of the problems is with using left is that if the graph isn't always going up or always going down, it's hard to tell if the area under my rectangles is bigger or smaller than the area under my graph. Meanwhile, what happens if someone wants right 6 for the same thing? And this is usually what they'll have us do. They're not going to make us draw the whole thing again. We're just going to try to draw it in a different color and see what happens. Now, all the sides are exactly the same. What I need to do is I just need to draw the rectangles and color them in a different color. So I go to my first little interval here. I want to go to the right end point instead of the left. I go up to the graph right there, and the height of this dot is going to be the top of my first rectangle for right 6. And I guess I'll try to draw that sort of like that. And then I'm going to do that for the next interval 2. I go to the right end point, I draw the top, and I'll draw that in. The next one, I go to the right end point, which is only here. I go over, I go like this, like that. I go to the next right end point, that's right here. This one's actually slightly above the graph, like that. I go to the next one, I go to the right end point, I go like that. Ta-da. And I do the same thing for the last. And you can see that drawing left 6 and right 6 usually isn't bad. I've never seen anyone actually ask for any more than that. But 6 can be very telling. You can get a lot of insight from 6, and it's something we should be in the habit of, is someone handing us a graph and asking us to draw some rectangles on it. Now, the next thing I want to talk about real briefly is what happens if the rate is negative. So let's look at a couple. What happens if the rate is negative? Well, let's start with a constant one first, because that's the easiest thing we can do. I'm just going to draw a thing like this. In fact, let's not draw that one. Let's just keep it over to the right so I don't get all screwed up. So I'm just going to draw like this. I'm going to draw like this. And I'm just going to draw a constant negative velocity. So it's going to go like this. Why don't we just say it's a negative 10? Yeah, that's it. Like this. Now, the problem is, remember what we did before, right, is that we took rate times time. If I take rate times time here, and why don't we go like, say, 5 seconds, and we can make this minus 10 meters per second, like that. If I multiply the rate times time, what I'm going to get is minus 50 meters. well, how can I possibly have minus 50 meters? Especially when I'm thinking I'm multiplying length times width. I'm getting that. Well, first off, you're seeing I have a rectangle that's under the x-axis instead of over the x-axis. You can see I actually have a rectangle that's above the rate graph instead of below the rate graph. And you see I'm getting a really creepy answer like minus 50. We're going to try to put all these together in just one more example. But the minus 50 should be, remember this is a position change. This is a position change. So here I'm not only saying that I traveled 50 meters, I'm saying I traveled 50 meters backwards or I traveled 50 meters down. When the rate is negative, actually things get more interesting, like say a little bit creepy. Let's draw something like we did before. Just draw something negative. How if I just do something like, you know, wiggle, wiggle, wiggle like that, and try to draw something like, let's say right 4. Just so I can draw it and see what happens. Now, to draw 4, I know I'm supposed to have 4 rectangles, so I chop this up and do 4 subdivisions. I know I have to have sides, so I draw the sides, draw the sides, draw the sides, draw the sides. And now in each little subdivision, I'm supposed to go to the right endpoint. That's for this one, the first one, that's right there. I go to the graph, whoa, that's way down here, right? But this is the height of the rectangle, so I'm going to go like this. Like that. Now, first off, you can see, why did I do that? Because I was just supposed to multiply rate times time. The time went this way, the rate went this way. That forced me to draw that rectangle. Would I feel better if the rectangle was above the graph? Well, not necessarily. What we're going to see here is that if I'm thinking that this box right here is rate times time, so it's a distance traveled, it's simply more distance traveled than the actual distance traveled, and it's actually more negative. So this would be a lower estimate of the change in position. Right 4 here would be also like this. Right 4 here would be something like this. And finally, the last one will look like this. Yes, I think here what's going to happen is right 4 is going to be a lower estimate for the what we're looking at the area. It is going to represent a distance traveled. It's just going to be a distance traveled backwards. One final example before we go. What if my rate graph looked like sine? And like that. I'm going to lie and pretend those actually look equal. Yes. What does this area represent? Well, we know that's the distance traveled forward. What's this? That's the distance traveled backwards. What does this whole journey look like? Well, I went forward, whatever the area of this actually was, and then I went backwards, whatever the area here would be, right? So if you're actually going to just do the rate times time, rate times time, rate times time, and add them all up, right, the sum here would wind up being 0. And we can see that that's not distance traveled. We can see that it's the change in the position. If someone wanted to make me find distance traveled, I would take the area here and the area here. But if I had to start just using left sums or right sums, all the left sums over here would give me positive answers. All the left sums over here would give me negative answers, and they would essentially cancel out. So when the part of the graph's on top, part of the graph's on bottom, it's going to be this distance forward minus this distance backward. And that's the end of this part.